Thank you for joining another exciting vibration research webinar. In previous webinars, we have discussed how to gather good vibration data, correlate it to real-world service life, and use it to develop a good vibration test profile with the fatigue damage spectrum, FDS analysis tools, and vibration research software. Today, we are going to take it one step further by talking about rapid failure mode precipitation testing, better known as RFMPT, and how you can use it with vibration research tools to ensure robustness in your product. We will explain what RFMPT is, how to develop an RFMPT test plan, and why it is an important aspect of product development. Doing this will not only make your vibration tests more meaningful, but will also provide realistic insight as to whether your product is ready for release to commerce. Please feel free to use the chat feature to let me know if you have any questions or comments during the presentation. Your feedback and questions are much appreciated, and we will be sure to get back with you after the webinar. Since vibration research's founding in 1995, the company has brought many innovations to the vibration testing arena. First, in 1995, field data replication was developed to replicate field environments in a non-iterative process, allowing tests to reach full level quickly, saving our customers time and money. Then in 2005, Kurtosion came out, and it's a patented technology that adds the effects of real-world kurtosis to a random waveform, allowing the peak accelerations to reflect the real world even around resonances. FDS generates random vibration tests based on using field data, thereby approaching a real-world environment as closely as possible in an accelerated testing timeframe. IDOF improves the accuracy and reliability of the short-duration random tests commonly used for expensive launch systems and complex payloads. STAG, or Sign on Random Test Generation, is specifically for developing vibration tests for products that live in environments with dominant sinusoidal content, such as engine environments. Most recently, TrueClip was introduced to reduce high sigma peaks on the shaker table. This clipping method applies to the control measurement and minimizes the chance of exceeding maximum acceleration, velocity, or displacement limits on your system. Vibration Research designs and manufactures vibration control and data acquisition systems for vibration testing on electrodynamic and servo-hydraulic shakers. The VR9500 is scalable to 128 channels, and its features include a sample rate of up to 200 kilohertz and 2 outputs. The VR10500 is our high channel count control hardware for vibration and shock testing. It is scalable to 512 channels with a sample rate of up to 256 kilohertz and 4 outputs for multi-shaker testing. VR controllers are compatible with all electrodynamic and servo-hydraulic shakers. The VR9500 and VR10500 also function as data acquisition devices. The Observer 1000 represents a new generation of technology for field data collection and analysis. Designed for mobile use, it is compact and weighs just 1.5 kilograms. It is also battery-powered and has an integrated SD card for data storage. The device supports test configurations with up to 16 channels, using a smartphone or tablet via a wireless connection. After setup, users can monitor and control tests wirelessly or let them run autonomously. We also offer a small collection of low-force shaker systems sourced from various manufacturers. So let's get started with our topic for today. RFMPT stands for Rapid Failure Mode Precipitation Testing. While in many ways RFMPT is similar to highly accelerated life testing, or HALT, RFMPT's aim is to not only identify product weaknesses, but to find them in such a way as to understand the likelihood of failure when the product is in your customer's hands. It also does not require special testing equipment and can be adapted to what is already available in your lab. RFMPT is a test to failure that can be used at any time throughout the product development cycle, from proof of concept to post-production verification and validation. RFMPT is an excellent way to run A/B comparison tests that are needed to prove out a design fix or confirm that a cost savings idea does not lead to warranty headaches down the road. As an integrated process of an overall product development plan, RFMPT is an efficient and cost-effective way to track reliability growth. Because the RFMPT philosophy lends itself so well to A/B comparisons, it is ideal for quickly and confidently validating manufacturing process changes, new downstream suppliers, and late design changes without the need for long-duration or hardware-intensive testing. As a test to failure, RFMPT demonstrates robustness to harsh end-use environments and customer usage. RFMPT is also a useful add-on to success-based validation test plans. After your test parts pass success-based testing, RFMPT can be applied to a subset of test parts to benchmark robustness. RFMPT is an adaptable, combined environmental test philosophy that also can be used to work out bugs in more targeted test setups, confirm parameters used for digital twins, and to assure that hardware is ready for full validation test flows. Finding and fixing problems before investing in producing large numbers of prototypes is a huge cost and time savings opportunity. RFMPT can identify design weaknesses anywhere in the product development cycle, whether early in the concept phase or as a way to ferret out manufacturing defects before production, or for continuous improvement once the product is in the field. Looking at a typical product development cycle, on the definition side, the statement of requirements should identify all performance, safety, and reliability requirements for the product in the specific customer application it is designed for. A comprehensive DFMEA, or Design Failure Mode Effects Analysis, should call out RFMPT testing in the proof of concept phase. Here it can be used to root out obvious design flaws, confirm upper and lower environmental operation points, and to establish what the destruct limits are for the design. This should be done early and with a relatively small number of parts on test and repeated as failures are identified and proposed solutions evaluated. This is also a good time to test just elements of a system, such as a circuit card or a cooling loop seal design. Once a design is past the proof of concept phase, the DFMEA should use RFMPT as a design control for early prototype testing and as a preventive control to provide realistic boundary condition for digital twin analyses. On the reliability growth side of the product development V-cycle, RFMPT becomes an important tool for shaking down test hardware before producing lots of prototypes for full-blown validation testing. It is also an important element of the PFMEA, which is the Process Failure Mode Effects Analysis, to ensure, in terms of minimal time, minimal hardware, and minimal lab resources, that process changes, late component or supplier substitutions, or minor design changes are directionally correct and robust against failure in the end-use environment. The RFMPT test philosophy also provides post-production confirmation of cost savings initiatives, warranty fixes, or other product process changes. The objective of RFMPT testing is to establish the design margin for the most common stressors that generate the largest amount of failure modes. This picture shows a good example of a full-blown RFMPT test setup for a complex DC to AC inverter for an automotive application. This test used a simultaneous 3-axis hydraulic rig for vibration tests that fits under a thermal hood, which for clarity is not shown in the picture. The thermal hood can use either focused liquid nitrogen or conventional refrigeration to achieve desired thermal ramp rates. You can also spray 5% sodium chloride to simulate corrosion environment. In addition to subjecting the test parts to real-world vibration and thermal stressors, the liquid-cooled power inverter units are also subjected to humidity while undergoing real-world electrical loads, simulating actual electric motor driving and regenerative braking conditions. 6 of these massive units can be tested at once on this particular test rig, all while being continuously monitored for intermittent electrical connections and other failures. Rapid failure mode precipitation testing is multi-environment, multi-input, multi-axial, correlated to the end-use environment, accelerated to reduce the test time, and adapts to available equipment. And that's a very important part of RFMPT, is that it is intended to make the best use of the equipment already available in your lab to validate and to test to the end-use environment any products that you have in development. Lastly, RFMPT is a test of failure. We learn from the failures, but we also want to do it in such a way that we know we have real failures and that we can correlate those failures to our design requirements and the end-use environment. As a test of failure, we can find many different failure modes in an RFMPT test setup. Thinking about testing a battery pack, we could find loose connections, structural cracks, coolant leaks, sealing breaches, broken welds, electrical shorts, loss of isolation, material degradation, thermal runaway, solder joint failures, mechanical wear out, and many, many more failure modes. And part of the fun of it is finding failure modes that we didn't anticipate in the DFMEA or didn't think could happen, and understanding that they're real because you know that the inputs that you're using for the RFMPT test are in fact related to the end-use environment. As with any test, the test must have proper scale in terms of whether we're testing a component, a subsystem, or a system. The RFMPT philosophy can be employed for any of these levels of testing. It is critical that the test replicates real failure mechanisms and failure modes by using inputs correlated through damage modeling to the end-use environment as defined by performance and safety requirements specified in the technical documents for the application. The operational parameters related to any mechanical or electrical cycling should, where possible, be included in the test setup. These characteristics should be well articulated in a comprehensive DFMEA with clear expectations for what inputs are critical and at what levels and cycle counts are needed to replicate a full life cycle of the product. In addition, which failure mechanisms drive which failure modes, how they are represented in the test setup, and finally, what performance criteria is used to establish a bona fide failure are critical to running a successful test. The last thing that we want is to get to the end of the test and be questioning whether something that we see is a failure or not. So it's very important to understand the end-use environment, how your test is correlated, and what constitutes a failure based on the design requirements before setting out to run any testing, but certainly before running an RFMPT test. Of course, the test should also be accelerated to minimize test time, but accelerated in such a way that foolish failures are avoided. Vibration research software and equipment assure that acceleration is appropriate in relation to customer environment. In the end, RFMPT is a test of failure that requires on-the-fly repairs to allow the test to continue in a controlled step-stress fashion to ultimate failure. This allows A/B comparisons and reliability growth tracking. Finally, RFMPT test results should be compared with a knowledge base in conjunction with math models to confirm that the validity of those digital twins is valid. Expect the unexpected and be sure to update your DFMEA with any learning that will speed up the next product development cycle. As mentioned earlier, RFMPT employs as many environmental variables as a product may require and a test lab has capability to simulate. The RFMPT test input should be correlated to the end-use environment using any of several damage models readily available for this purpose. We could go into detail on any of these models, but for now, let's just list them. For thermal cycling, the common model to use is a Coffin-Manson damage fatigue model. For thermal aging, an Arrhenius model, dependent on material properties for activation energy. Humidity, the Peck model. For vibration and mechanical shock, we use fatigue damage spectrum and the shock response spectrum. Both are available models in vibration research software. Mechanical cycling, it's important to know how your customer will use your product. So if you have a on-off switch, for example, how many times is that switch used and how do I replicate that in my test and correlate it back to appropriate number of cycles for our customer. Same is true for electrical cycling. And there may be other inputs not listed here that require some assessment to end-use environment, such as corrosion. Vibration research tools are adept for gathering data and correlating vibration and mechanical shock tests using the fatigue damage and shock response spectrums. If you have specific questions about these or need help figuring out how to get good baseline data, please put them in the chat or contact vibration research support and we will happily get back to you. The benefits of using field data and damage models to correlate your test to customer environment cannot be overstated. Firstly, field correlated models build confidence that identified test failures are probable in the field. They allow you to fix the right things for the right reasons. They are necessary for defining virtual twins or math model boundary conditions. And finally, they establish appropriate test acceleration factors. We want to be certain that our testing only produces true failures and for the right reasons. RFMPT testing progresses in essentially 4 phases. The first phase establishes that the parts on test are suitable by measuring critical performance characteristics at nominal design environmental corner points. We want to make sure that the parts that we put on test are fully functional and that we have a baseline to compare at the end of test. The second phase is pre-aging, which is generally exposing test parts to an elevated temperature for some period of time to isolate inherent material weaknesses in seals, solder, injection mold knit lines, etc. We use the Arrhenius model, damage model, to input one nominal life in our test. Pre-aging could also involve mechanical shock, mechanical or electrical cycling, or electronics burn-in, or whatever is appropriate for the product that you are putting through the RFMPT process. The heart of the RFMPT test is the combined environmental testing, especially vibration and thermal cycling. The vibration inputs are performed in an increasing step stress fashion in which each increasing step is correlated to one product life using the vibration research fatigue damage spectrum methodology. We'll talk more about that in a minute. Finally, an end of test full functional verification, identical to the initial functional verification, is performed on every part to identify latent defects, quantify degradation, and provide data for A/B comparisons and reliability growth tracking. The RFMPT thermal cycle is intended to expose the test parts to one cycle of peak hot and cold per vibration step stress cycle. In addition, thermal cycles with smaller delta T's are used for the duration of the vibration testing to accumulate as much thermal damage as possible. It is important to understand how the number of thermal cycles corresponds to accumulated end-use environment thermal exposure so that an understanding of field reliability can be gleaned and reliability growth can be tracked. Thermal characterization of test article ramp rates versus the thermal chamber is essential for verifying that the chamber is optimized for all test part locations and that true thermal cycling can be related to the correlated damage model. This is especially true if your product has any solder joints that are being tested. We want to make sure that the part itself is seeing the delta T's that we are prescribing. In this example shown on the screen, The chart is showing when during the cycle the test part is powered and when active liquid coolant loops that are incorporated in the product design are used during the thermal cycle to either aid in the heating or to avoid impeding the cooling. So this chart specifically is referring to the picture that I showed earlier of the AC to DC inverters in the RFMPT test, which themselves are in the application liquid cooled. And we want to be running the units while we're doing the RFMPT test in a realistic way, which means that we need to have the active cooling for the parts active and running. And that can be a problem if it's competing against the thermal chamber. So for that reason, we turn the coolant loop on and off at appropriate times to aid in getting the parts to the temperatures that we actually want them to achieve. Understanding these relationships between the test parts and the test chamber are necessary to optimize the cycle for test efficiency. One element that is very important for RFMPT is using appropriate vibration profiles. We will focus the rest of this webinar on how vibration profiles are used in RFMPT and how to make them for this purpose. For many products, this means having separate profiles by axis. One for vertical, one for lateral, one for fore-aft. Ideally, an RFMPT test is run using either an electrodynamic, hydraulic, or servoelectric multi-axial vibration system so that we can get all three profiles at the same time. However, if such a system is not available, various adaptations can be made using a single axis shaker by either enveloping the profiles, which is the least desirable, or working in ways to test each axis separately. In the example shown here, the product is being tested over the 10 to 2000 hertz bandwidth, with different amplitudes by axis, which appropriately excite various resonances based on vibration research, fatigue damage spectrum analyses. As shown next, the RFMPT process increases vibration amplitudes by 1.5 dB increments. The first or baseline vibration level in an RFMPT test subjects test articles to one equivalent product life as determined by processing measured data using the vibration research fatigue damage spectrum and accelerating the test time such that amplitudes are below the shock response spectrum limits. This is important to avoid foolish failures, but yet to maximize the acceleration of the test to minimize the overall test time. Running the first vibration test at this level establishes the likelihood that the part will pass performance, reliability, and safety requirements at the end of its life. However, RFMPT is a test to failure. Accordingly, if the parts survive the baseline level, the test level is increased by 1.5 dB and run again for a shortened period that ensures that the test parts are exposed to a second lifetime equivalent of vibration fatigue damage. In this example, the vertical profile from SAE J2380 vibration standard for electric vehicle batteries is used for illustration. Vibration View software easily scales a set of vibration test breakpoints by 1.5 dB or any other desired factor. The process of increasing the amplitude by 1.5 dB and shortening the test time to maintain one product life fatigue equivalent continues until enough unrepairable failures are achieved to apply a statistical analysis for reliability growth tracking. In this example, the process was continued for 6 vibration levels out to 7.5 dB. And in the Vibration View software, we can use this scaling, and we have a choice over here. You can pick dB, and in this case, I want 1.5 dB, and it produces over here a new set of breakpoints, a new GRMS level. And we can continue that as far as we need to. In this case, for illustration purposes at least, I went out to level 6 at 7.5 dB. Using the SAE J2380 vertical vibration profile as a baseline, we can see that the initial RFMPT level is run for 19.8 hours at 1.8 GRMS. At the 6th level, the test is run for 15.9 hours at 4.3 GRMS. So we increase the amplitude and decrease the time. Each of those test levels represents one product life. The time acceleration is based on the well-known formula for accelerating vibration profiles from GRMS levels. If you are familiar with the SAE J2380 standard, you will know that the vertical baseline test is only 5.5 hours long. However, because RFMPT correlates to a desired reliability target, a sampling plan is used that relates number of parts on test to how many product lives a part must survive to demonstrate a reliability requirement. For this example, I chose 6 parts on test with 0.9995 reliability at 50% confidence. And you can see on the chart at the right that that means that for 6 parts, we need 3.6 repetitions of our duration on our profile, which 5.5, which is the standard time, times 3.6 for 6 parts on test, gives us the 19.8 hours that we need to run the test. This concept was described in Vibration Research's January 2024 webinar on sampling plans, which can be easily found in the library on Vibration Research's website, along with a plethora of other great vibration knowledge, tips, and tricks. A correlated baseline vibration profile can be easily made using the fatigue damage spectrum package in vibration research software. Using measured accelerated data from your application or a surrogate application, or from somewhere else that you may be able to find such data, the acceleration data is first converted to velocity, as velocity can be related to fatigue. Next, the resulting velocity time waveform is run through a series of narrowband filters to generate frequency-specific waveforms that are rainflow cycle counted. Using Miner's rule and an appropriate SN curve for the material of interest, fatigue damage is quantified for each frequency, thereby producing a fatigue damage spectrum. The Henderson-Pearsall transformation is used to yield a PSD for a vibration profile that is correlated to the end-use environment. In the case of having multiple waveforms, we can also use those to combine them and make one profile. So multiple waveforms representing different events, such as highway driving, rough road driving, Belgian blocks, gravel roads, high torque, etc., can be combined in the fatigue damage spectrum software to produce an even better correlated vibration test. Using the product's material parameter, which is the slope of an appropriate SN curve, and setting the narrowband filter, the process on the previous slide can be executed. The target life is as defined for the product in its design specifications. It is the starting point for accelerating the vibration test to get the baseline profile that represents one product life in an accelerated test. The shock response spectrum package in vibration research software is then used to confirm that the vibration test is not overly accelerated so that we do not generate foolish failures or failures that possibly would not actually occur in the field. Again, a lot more details about how this is done is available in the library on Vibration Research's website. Finally, Vibration Research's patented Kurtosion can be used to more closely replicate the peak distribution found in the actual end-use environment. The FDS to PSD transformation yields a vibration test with a Gaussian distribution of peaks. In other words, a normal distribution of peaks In the real world, however, the distribution of peaks tends not to be normally distributed, but rather there are some peakiness going out in the tails. With the increased number of higher amplitude peaks that we get when we apply the Precipitation, the fatigue damage accumulates faster at the same overall vibration level, thus allowing for additional time compression. We can do this in our fatigue damage spectrum software just by clicking the Precipitation box, as shown here on this screenshot. VR software gives you the option to apply Precipitation time compression to shorten your test duration while making the test even more correlated to field conditions because we're actually incorporating real peaks. We're getting those real peak loads. So the keys to a successful rapid failure mode precipitation test is, first of all, good data. We can get good measured data using Observer 1000 or other data acquisition system to measure data on our product. And that's for vibration data, but we also need thermal data, ideally, corrosion data, humidity data, electric load data, number of mechanical cycles, etc. So we need good data, or the best data that we can have available to us to correlate to that end use environment. From that good vibration data, we need to make a good vibration profile because, again, the heart really of the RFMPT process is that vibration profile. We use the fatigue damage spectrum to generate an accelerated baseline and confirm that it is accelerated maximally without producing foolish failures by looking at the shock response spectrum for that same data. Then we put that into a good test setup. So a good test setup is one that has appropriate fixturing, that has good fixturing, that is a system that is well controlled in a vibration environment, and that is representative of all of the important environmental variables that we need to look at for a good RFMPT test. That test should be correlated to requirements that are specified up front as for performance, safety, and reliability. And the test should be tied into a sampling plan so that we understand that we've met all of those targets. And that would be what we call the robust reliability, is when we take our parts and we ultimately bring them to failure, and we learn from a comprehensive design review based on test results and reporting of what those failures are, and we propose fixes, repeat the process to do the A to B comparison to show that we're directionally correct and that we have reliability growth. So RFMPT is done early in the process on just a small number of parts to establish operational limits, destruct limits, and as time goes on, we use more parts and correlate it back to reliability. And as we get out into the field or we have late design changes, we have a baseline. We have a criteria to do an A-B comparison on any design changes or process changes that ensue at any point in the product life cycle. So in conclusion, RFMPT, rapid failure mode precipitation testing, is applicable throughout the product development process. The testing is correlated to the end use environment. That is key. The testing does not require special equipment. So again, the idea here is to be able to use the equipment that you have in your lab in an optimal way with the environmental inputs available to you that make sense for your product, and to learn from that as quickly and as efficiently as we can, and to have a baseline for doing A to B comparisons. Vibration research software allows you to develop the test confidently, and vibration research hardware allows you to execute the test accurately. That completes our webinar about rapid failure mode precipitation testing. As you can see, we are laser focused on vibration testing, and our products have an unmatched set of tailorable capabilities. If you have questions or comments or want to provide feedback, please contact us at support@vibrationresearch.com and we will happily get back to you, or you can call us at the number on the screen. So thank you for attending this webinar and have a great day.